On the left-hand side over here, I have EH plus H delta E minus EH is equal to negative A delta B over delta T. So this gives, and this, oh, actually, what is the area?
Delta X times H.
Yes, it's a rectangle, length times width. I'm getting a lot of blank stares here. This is a rectangle. It is a physical distance. It has a length and a width. People seem to be getting thrown by that. Why don't I drop back and what are the questions here? Why is there so much silence?
I think because it's 7:35. Yeah, but not really. That's what I'm saying.
On the left-hand side here, EH cancels out, so I'm left with H delta E. And that's equal to negative H delta X times delta B over delta T. I'm going to leave that there for right now. I'm going to divide both sides by delta X. My H's cancel out, which is nice. So I'm left with delta E over delta X equals negative delta B over delta T. And this is where we started. So, what is delta E over delta X? So given our function for the electric field, what is delta E over delta X? For those who've had calculus, what's the first derivative? For those who haven't had calculus, refer back to what we did at the very beginning of class.
Delta E over delta X would be E sub 0, or negative E sub 0 sine.
Oh, we're starting with sine now. So, well, before in class we started with cosine, but we're starting with sine.
Okay. Then it's just E sub 0 cosine kx minus omega t.
Left one thing off.
A. Right? No.
No, the amplitude is E sub 0.
Okay.
Okay. Because don't forget, when you do the slope, this, if it's with respect to position, then you bring the k out every time. Or with respect to time, you bring out negative omega every time. All right. So that should be equal to the negative of this right here. And there's our formula for the magnetic field. So E sub naught k cosine kx minus omega t is equal to the negative of the change in B over the change in time.
B naught omega cosine kx minus omega t.
Left one thing off.
Would that be negative omega?
Yes, it would. Negative omega is the prefix, is the coefficient. So a negative just up here, which makes that positive. So let's now get do some canceling going on here. What else can we get rid of?
Cosine value.
And so after all of that, we're left with this E sub 0 times K equals B sub 0 times omega. Therefore, omega divided by K, bring the K over to here and the B sub 0 over there, is equal to E sub 0 over B sub 0. In other words, the speed of the electromagnetic wave is just equal to the amplitude of the electric field divided by the amplitude of the magnetic field. And for those of you who are thinking, oh, this ended way too soon, we're halfway there. We have to do it again, except then we'll be using Ampere's law with the Maxwell correction. Questions? All right, I need to erase stuff. Presumably people have this part down already. We'll leave that. And we'll leave that with black marker that way, it's really dark. This one. Oh, there we go. All right, I'm going to erase that stuff in just a second. So we now have, starting with Ampere's law, B dot delta L is equal to mu naught times the traditional current plus mu naught epsilon sub naught delta E, delta phi sub E delta T. Just like before, we need to create we're going to be doing the magnetic field, adding up the magnetic fields along a path, and so we have to create the path. So looking at our diagram again, where we've sort of exploited it, we have electric field going up, we have magnetic field coming at you. All we're going to do from looking at it, we're just going to look at it from this point of view right here.
Yeah.
So now the magnetic field is going up, the electric field is going into the board, because they go together. We are not dealing with actually any moving charges in terms of once the wave has been produced. Therefore, this is 0 right here. This is the current based upon a moving charge. So let's see. So I'm taking 2 points. I got my magnetic field here and my magnetic field right beside it. The distance between them this way is delta x, and the height is h. This is b plus, this is b right here, b, and then b plus delta v. The path we're going to, and my electric field is going into the board. And we are going to do it, basically it's a right-hand rule kind of thing. My electric field's going into the board. We're going to do our loop. We're going to start here, and we're going to go clockwise in our dot product here. So I'm going to label this A, B, C, and D. And so this becomes B of A dot delta L of A plus B of little b plus delta L of little b plus B of C plus delta L of C plus B of D plus, sorry, not plus there, those should be dots, dot, 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 delta L of D is equal to mu naught epsilon sub naught change in E dot A All right, so let's do bit by bit. What is B dot delta L sub A?
Would it still be zero?
The A is along here now.
Negative B times H.
Wait, say it again?
Negative B times H, maybe?
Why negative?
Oh, never mind, positive,
Why positive?
because it's going clockwise, it's going with it.
Yeah.
Right now.
So in this section right here, we're both going up. So this would be BH. All right. B sub B dot delta L sub B. So we're now on this path right here.
0.
All right. Less than 0. B sub C dot delta L sub C. So now on this path right here, heading down.
That's negative.
Yes, that is negative. Negative what?
B plus delta B times H.
And then the last segment, we're going from the lower right to the lower left corner, getting back to where we started.
Zero.
Yeah. Equals, over here, my area vector, we'll make the area vector same direction as the electric field. And so we end up with mu sub naught, epsilon sub naught, A, times the change in the electric field over the change in time. On the left-hand side here, we have BH minus BH minus H delta B equals mu naught, S sum naught. What is the area of this rectangle?
Change it back times A.
Say it again?
Change it next time to, or H, sorry.
Thank you. All right. Times H delta X. And then the change, we'll leave that as is for right now. Over delta T. So what I'm left with is negative H delta B is equal to mu naught epsilon sub naught H delta X times delta E over delta T. Now let's get rid of some stuff. First round of getting rid of stuff. H goes away. I'm going to bring the delta X over to the left-hand side. And so I'm left with negative delta B over delta X equals mu naught epsilon sub naught delta E over delta T. Pretty sure it's where we're supposed to be, but let me just do a quick double check to make sure that we did not end up with a negative sign in the wrong place. No, doing good. We've been here before, or somewhat very similar. What is delta B over delta X? Really cool if you could do it in unison right now.
4, 3, 2, 1.
There's that psychic vibe there. There's our formula for B right there.
Yeah, it would be.
We're looking at the slope with respect to position.
Ready, 3, 2, 1.
E sub naught.
B sub dot sine. KX plus. Kidding.
You're just stating the formula right there.
B sub naught.
Cosine.
Okay, it'll be cosine.
Yeah, I can't.
It's
remember.
B sub naught X, or, okay.
Then cosine KX minus omega t.
It's probably as close as I can hope to unison right there. All right. That's equal to mu sub naught, epsilon sub naught, times delta E over delta T. So now we're up here, we got this.
Man, this time change is stupid.
You're sliding behind it, right?
Rude. There's the cosine too.
E sub naught.
It will be a cosine also.
sub naught omega cosine
B sub naught,
omega. Omega?
close,
Negative omega.
negative omega.
Negative.
All right. Now what can we get rid of?
Cosine.
All right,
Stupid time.
cosine goes away. We get rid of one more thing. Somebody might have said it and I missed it. Let's write what we have here. So I got negative B sub naught K on the left-hand side. The right-hand side, I have negative mu sub naught, epsilon sub naught, B sub naught, omega. There's a minus sign right there, but not just below up front.
You could take away the minus sign.
Yeah. So, omega over K. So bring the K over here and everything else to the other side is going to be equal to B sub 0 over mu naught sub 0, epsilon sub 0, big E sub 0. So what we have here is that the speed of the electromagnetic wave, and we'll just use the letter, traditionally the letter C is used for it, is equal to omega over K, which is equal to E sub 0 over B sub 0, which is equal to, from what we have now, B sub 0 over E sub 0 mu naught epsilon sub naught. If I now look at this right here, I'm going to get the E's and B's on one side and my constants on the other. I get E0 squared over B0 squared is equal to 1 over mu sub naught epsilon sub naught. Recognize E sub 0 squared over B sub 0 squared is just the speed squared. And therefore the speed of an electromagnetic wave is 1 over the square root of mu sub naught epsilon sub naught. Which is 1 over the square root of 4 pi times 10 to the negative 7th. Tesla meters per ampere, I believe. Times epsilon sub naught, 8.85 times 10 to the negative 12th. Coulomb squared per Newton meter squared. And so I'll be kind enough to do that.
What does it equal C squared?
What, sorry?
Where do you get the C squared from?
We established that the C is just the speed.
Yeah.
So from the first time we went through it, we had the speed is equal to basically the magnitudes of the electric field and magnetic field. Here I have just that squared.
Okay.
So that's where we get it from.
Okay.
And what you get?
Somewhere around 299 million, something. 2.99 times 10 to the 8. It's 2 hours.
Units?
Meters per second.
Yes. If you work through all of that, you end up with meters per second. All right, so therefore, Maxwell gets to this, and then in humility, actual humility, says, this is so close to the experimental speed of light that I suspect this light is an electromagnetic wave. He was not bold enough to make the absolute claim that it was an electromagnetic wave, you just suspect it. And he turned out to be right. This is 1870s that this is going on, that he does this. So the US had just finished its Civil War, and we were in the midst of rebuilding for that. So no real science going on, especially war doesn't promote science, usually promotes engineering. So now, this was considered a great achievement, and some physicists looked at that and said, you got a mistake in here. So the question is, what would physicists say is missing? An issue that won't be resolved for another 30 years.
Are we not taking into account what it's moving through?
If you're taking into account what it's moving through, then you would drop the sub-zeros there. So, but even going through a vacuum, the physicists, some physicists, the establishment was going, you've got a mistake. This is not some high concept that we're talking about here. This is something we have actually talked about, especially in the first semester. It's like day 1 or day 2 of the first semester course.
Yeah, the only thing I remember from the first semester is your question.
What's that?
The first thing I remember from your, like, the first days of our first semester was like, how do you solve this? You know, you literally just wrote the whole thing. That's what I remember.
Good times.
Good times. Easy times.
But you
I
said,
think about easy times.
you said if direction was eliminated, this sub-naught values, they wouldn't matter, right?
If the medium, this is going through the vacuum of space. If it were sent through a medium, then the zeros, you would drop the zeros and it would be specific to whatever the medium is.
Do you have to account for magnitude?
No, you don't. That was not the big issue.
Something about speed.
Something about speed.
Oh my god.
Speed and direction? No?
Now the direction, it turns, I don't go through that derivation. The direction that it's going to travel is the same direction as E cross B. So E cross B, that's the direction of propagation. It creates something what is known as a pointing, P-O-Y-N-T-I-N-G, pointing vector. So direction is not the issue. There's an issue with the actual value for the speed.
What's
You're about to say something, Joe.
the speed of light?
It's about that. It's
Oh, okay.
about 299 million.
They want to use light years.
No, it was not a unit issue. All right. So early on in 151, when we start talking about speed, one of the questions I ask is, how fast are you going?
Oh, in reference to something else?
Yes. This equation doesn't have anything in there about the observer. That's where the mistake was. This is where the supposed mistake was. A guy named Lorentz, who was one of the bigwigs at the time, basically spent the next several decades trying to figure out, explain why it doesn't show up. Then Einstein comes along. Einstein says, let's pretend that there is no mistake here. That the speed of light actually is this, regardless of how fast the observer is going. No matter what the reference frame is, as long as you're not talking about the reference frame of light itself. Whatever the reference frame is, that's the same speed no matter what. And then he took that to the next level. Set up a thought experiment. You have a box here that is traveling along at some speed v. there's a mirror up here.
I have this box on there.
What's that?
Box on floor.
Box on where you get
For Max.
Should I put it on a swim? No. This thing's traveling at some speed, constant speed v in that direction, so constant velocity. And it shoots a beam of light up. So the light basically, since there's a horizontal motion, the light's basically gonna come up here, hit the mirror, and then bounce back and hit the box again as the box moves to the right. So this is what we'll call the lab frame. And then he said, suppose you were in the box frame. Suppose you were in the point of view from the box. The light would go up and then come straight back down. So box frame. Or rest frame would probably be better wording. If both of these are true and the speed of light is the same in both cases, what is the implication?
Speed is the same when the box is moving. This speed is the same.
The speed of the light going here to here, and the speed of the light going here to here is the same.
Is the same, yeah. Regardless of whether the box is moving or not.
Right.
Yeah.
So what's the implication? There's a rather consequential implication if the light travels the same speed in both cases.
Is it a famous equation?
It is in physics circles.
E equals mc squared? No.
That actually, that and about 3 days worth of math. We'll get you there. I was hoping for the more immediate step.
It's traveling the same distance?
No, this is traveling just up and back, and this is traveling a different distance.
What's a famous physics equation?
Time is relative.
Yes.
Yeah.
They travel at the exact same speed for different distances. The times are not the same.
Okay.
That is the implication. And then 5 days of math later equals mc squared. I have done the derivation of E equals mc squared in the calculus class. It is a grueling 3-hour affair with calculus. I don't do it every semester because some semesters I just don't have the energy for it.
So the thing is like, time stops at the speed of light, is it?
Yeah, time would stop at the speed of light. But this, what happens here, if you go through what the heck, let's go through the math. It's a question of whether I do it now or do it in a month or do it in a couple of weeks.
I didn't even. Guess what?
I'm sorry.
No, we were gonna do it, it's just a matter of when.
See, it was in I just made it faster.
All right, let's see if I can do this without traveling in a circle here. All right, so the light is traveling up and down like that in the lab frame. We'll call this in some amount of time t. Down here, we're gonna call this t sub p. The p is for proper, this is proper time. So this distance from here to here is, we'll just use h. And this distance from here to here, well, it's traveling at some speed v for time t, so this is just the distance vt. Distance times time. Or better, speed times time. In the second frame, it's just going up and back. It goes up a distance h. And so the distance that light travels is going to be 2h. The speed of light, c, will be 2h divided by t sub p. So it's distance over time. Up here, I've got a triangle here. So the distance that travels here, probably delta x, so p. So delta x, yeah, so p there. So delta x here would be this is 1/2 VT. This is h, little Pythagorean theorem. This is h squared plus 1/4 v squared t squared. So the distance it travels is 2 times the square root of h squared plus 1/4 v squared t squared. And so the speed of light in the lab frame is just that divided by time. So 2 square root of h squared plus over time. And those speeds are the same. Now, h is the thing I actually want to get rid of. I want to figure out what is the relationship of time based upon the speed. And so I really want to get rid of h because it's rather arbitrary how high up the mirror is. And so from this right here, we have h is equal to 1/2 c times the proper time. Plug that into the equation up here, and I get c is equal to 2 square root of 1/4 c squared proper time squared plus 1/4 v squared t squared over t. I got a 1/4 as a factor on both terms in here, so I'm going to factor that out, and when I do a square root, it created 1/2, which cancels out with the 2. In other words, I'm making the claim that 2 times the square root of 1/4 is equal to 1. So this becomes the square root of c squared proper time squared plus v squared t squared over time. The radical is a nuisance, so I'm going to get rid of it. I'm going to square both sides, not just make it go away. So I have c squared equals c squared tp squared plus v squared t squared over t squared. I want to get rid of the fractions for now. So c squared t squared equals c squared tp squared plus v squared t squared. I'm going to solve for t because I know where I'm heading on this one. So I'm going to bring this over to the other side. So I have c squared t squared minus v squared t squared equals c squared tp squared. Just algebra here. Factor out the t squared. So I have t squared, c squared minus v squared equals c squared tp squared. And then bring this over. So t squared equals c squared tp squared on top